Okay. So a higher order example, say 3, is the following. Let f be from R2 into R be differentiable twice. You can assume that has second order continuous partials. Okay. Because this implies twice differentiability. Okay. Now the problem is the following. Z of st is f of st and s squared t squared. Okay. Question is, find the derivative of z, but the second derivative with respect to t first and then s. Okay. Now to find this, of course, we have to calculate del z, del t first. But this, of course, is a chain rule, and it's a total derivative formula, but z is not a function of t, actually it is, but f is not a function of t directly, so we have to modify it a little bit. You can use a tree, for example, f depends on 2 variables, and they depend on s and t, s and t. Okay. Now, this makes sense. So, the derivative of the right-hand side with respect to t means that you calculate these 2 branches because you only have t in these branches. So this would be directly derivative of f with respect to u, that is the first variable, and derivative of u with respect to t, where of course u is st, and v is s squared t squared. So derivative of u with respect to t is meaningful, that is u sub t, plus, it's a partial derivative again, because you have an s here. And f2, v with respect to t, this time, in the second branch. This is how we reach t using the 3. But, of course, it's a direct application of the remark a minute ago. It's a total derivative formula. When s is constant, okay, f is a function of uv. uv are functions of t only, because s is constant. So this is just the total derivative formula. Okay, that's fine. Now, let us take the derivative again with respect to, this time s. So that would be, okay, I'm copying from that, f1 ut plus f2 vt. Now to take the derivative with respect to s, now of course t is constant. Okay. Now the important thing is to determine whose functions f1 and f2 are. What do we have there? Well, f1 is the derivative of f with respect to its first variable, which we said is u. So this is f sub u. But what are the variables in f sub u? Well, f was a function of u's and v's, and we have fu. So v is a constant. But it's there. It did not disappear. So fu is a function of u and v still. So here, let me give the note. Okay. Now, in calculating fu, v is a constant. So to find fu, v is constant, and we differentiate. But v does not disappear. A very simple example is the following. Say fuv is, say, u squared vq. Then f sub u, v is constant, is 2u vq, which of course is again a function of u and v. So we have to be careful there. That is to say, fu is a function of u and v, and u and v are functions of s and t. So on the left-hand side, we have s and t at the end. So when we want to calculate this product, u of t, of course, is s, and v of t would be 2ts squared. Okay. But the others are functions of u and v, which contain s at the end. Therefore, this product is a product derivative, actually, because we have s everywhere in this formula. Okay. So, by product derivative, we have derivative of s, because t is constant, of f1 times ut, which happens to be s, and then f1 times the derivative of ut with respect to s. Well, this of course is uts, but ut is s, so this derivative is 1. That's easy. So we have a product derivative for the first part. For the second one, we again have a product derivative, only instead of f, we have f2 now. So this would be, we are differentiating with respect to s. So it is del by del s f2, derivative of the first one, times dt, plus f2 times derivative of vt with respect to s. Well, we can directly calculate that. It's 4 st. Okay. Now, when we look at the final formula, we have already calculated these things. Now, for f1, that is derivative of f with respect to its first variable, unless we know what f is, we cannot go any further, because it just says it's a function of two variables. You consider derivative with respect to the first variable, which happens to be u, and here, of course, it happens to be v. There are no chains left, so we can't do anything there. But for del by del s f1, we can do still something. That is, the primary variables in f1 are u and v. Well, u and v are functions of s. So there's a chain. So we can calculate this in detail. Let us do that. Now, for this derivative, okay, we can do something because f1 is a function of u and v in the first place. And then these are functions of s and t. I can use a 3 because this is a derivative of first degree. That is, it's not a higher order derivative. But instead of f, we have f1. So we have to be careful. What was it after all? It was the derivative of f1 with respect to its first variable. Namely, it is del y del u. I can use the 3 here as well. I want the derivative with respect to s, so I want these two. So it is derivative of f1 with respect to u, and then derivative of u with respect to s, plus derivative of f1 with respect to v now, and derivative of v with respect to s. But I could have done this by using the total derivative formula directly, because f1 is a function of two variables, and they are functions of s and t, but t is constant. So there is only one variable s, so I can use total derivative formula. This is exactly what it would tell us. But you can do it from this tree as well, okay? Or by using total derivative formula. Okay. Now what can we say here? Obviously, f1 is the derivative of f with respect to u, and we are differentiating it once again with respect to u, which means we take the derivative of f 2 times with respect to u. Well, unless we know f, we don't have a chain here, so we cannot do anything more than that. So I can write here, it's the derivative of f with respect to the first variable again. Or I can write fu times, well, del u del s. Well, I know what u is, so I will not calculate those in detail. For the second one, I have f1, but then I take the derivative with respect to its second variable, so it is this, which of course could be written in this form. And finally, similarly, for the derivative of f2, okay, the function is f2, not f1, so I can use the same formula with f2. So it would be f2, and then the derivative is taken with respect to the first variable, and then us, f2, now with respect to the second variable, vs. Of course, you can write vu and vu. And these can be calculated directly. So putting everything in place, we get the result. Now, the tree, as I said, works only for first order derivative, as in this case. Okay. It is first order derivative of f1, not f. But that's immaterial. I have a function of two variables, which is a different function than f. I can carry out the process. But before that, recall we came across product derivatives. Now, a product derivative is not taken into account by a tree. It doesn't tell us anything about that. So if the order is higher than 1, we should use total derivative formula and product rules in detail. Okay, now we will consider next how we can apply these ideas to implicit differentiation. Okay. Since implicit differentiation is quite dependent on the chain rule, we can have such examples in functions of several variables as well. Okay, let me say implicit differentiation here. Well, suppose f of xy is implicitly defined by, say, zx plus sine z minus xyz plus xy is 1. And our point P0, which satisfies this, is 1, 1, 0. Okay. So because z is a function of two variables, I can talk about the derivatives of z. So the question is, find del z del x at P0. Okay. Or whatever we want. Now, the principle is exactly the same as in the case of one variable. Of course, the question, is it possible to define such a z by such an equation at this point, is a little bit beyond our scope. It's called the implicit function theorem in mathematics. If certain conditions hold, we can do it. Okay, I will not go into that. I will assume, indeed, z is defined by this. If we solve z from here, which we cannot explicitly, okay, we will get a function that is assumed. The problem is to find the derivatives of z. Well, in doing this, we keep in mind that z is a function of xy. So let us start differentiating. Okay, how? We want del by del x, so y is constant. Now what does this tell us? Well, let us start from here. X is the variable, but z is a function of x. So, but y is constant, so it would start del by del x z times x plus z times derivative of x, which of course is 1. This is the product derivative of the first term, plus derivative of sine z, which would be cosine z, times derivative of z with respect to x again, minus xyz. Well, xy times z, and xy has a derivative, y, times z, plus xy times derivative of z. Of course, all these derivatives are taken with respect to x, So the derivative of xy with respect to x would be y times the second one. So it's again a product derivative. So these are all product derivatives. Okay. And then we have xy. Well, its derivative is easy, just y. And on the right side, we have 0. So from here, we can solve del z, del x. Okay. Clearly, we have it occurring at 3 places. So here, we would have just x plus cosine z, okay, and minus xy del z del x. This takes care of this term, and this term. And the remaining part goes to the other side. So that would be minus z and plus zy and minus y. Okay. So this is our function. Of course, if we want the value at 1, 1, 0, we should put that in place and then get it. So del z del x at p0 would be, well, z is 0 and y is 1, so that's minus 1. And z is 0, so this is 1, 2, and minus 1. That makes 1. And so we find it that way. Okay. Well, we could also, by the same method, find the derivative of z with respect to x. So similarly, del z del y can be found. Okay. Well, once we have the expression for del z del x, we don't need to solve that equation. We could directly differentiate again if we wanted. Okay, we can even find and so on. But of course, that would be quite tedious. It would be a long calculation. I will not do it here. Okay. Well, an application of this idea to an implicitly defined function of one variable is quite interesting. Now, suppose f of xy defines a differentiable function y equal to f of x. We came across such problems in 1.19. But here we have a different setup. So, if f is differentiable, then apply total derivative formula to both sides. Meaning, of course, x is a function of x, y is a function of x. So, okay, total derivative formula says that left-hand side is f sub x times dx by dx plus f sub y times dy by dx, which of course is f prime x. So, f prime x would be minus f sub x divided by f sub y. Okay. Well, at the wanted point, we can evaluate it. Note that this points out to one interesting thing. F sub y should not be 0 at the point. If it is, we have trouble in formulating f prime x using this formula. Well, this is an important hypothesis in the implicit function theorem. As I said, we will not go into that, but for example, as a simple one, let us understand what that means. Consider fxy as x, let me get it correctly, so y cubed minus x. Okay. Then fxy equal to 0 defines a function. Defines y, this, suppose we don't know this, so I will not write that. Defines it as a function. In fact, it is the cube root function. Okay. Then, the derivative of y, namely f prime x, that is dy by dx, would be minus f sub x over f sub y, which is minus f sub x would be minus 1, and f sub y would be 3y squared. Okay, so this is the derivative. Well, you can, if you want, substitute back to x. Actually, because we know what y is, we can directly write it here. So, in fact, this is 1 over 3 y to the power, well, what happens? Y is cube root of x, so it is x to the power 2/3. Okay. Now, because at the given point, okay, this of course means that this is in the graph of f, because 0 cube root is 0. Okay? At this point, okay, the derivative, okay, cannot be defined by this formula. Because f sub y is 0. So, f is well defined, it's a continuous function. Cube root of x is a nice continuous function. It has a derivative everywhere, but not at 0. So, by this formula, we cannot find it. But a better reason behind it is that there is no derivative, okay, of y with respect to x at 0. Okay? So that's why we cannot find it. So this tells us that if f sub y is 0, it tells us that we cannot solve the system for y as a differentiable function. We can solve it as a function, but not as a function with a derivative. But as in here, but sometimes just as a function. Okay. Even though it's possible, it will not be differentiable. Okay. So then, we can now use this formula to calculate derivative of an implicitly defined function, because it's easy to calculate these things. Okay. Well, this will conclude our discussions on the chain rule. In our next video, we will consider more geometric aspects of derivatives of functions of several variables.